Welcome back. Okay, so we have been deep into the wilderness of complex functions and complex variables, derivatives and integrals, Cauchy, Cauchy integral formula, and we are just about out of this wilderness. There is one more lecture, so I believe I have timed this so that this is the 13th lecture in this series on complex analysis. This should cover about a 2-week course. And I've kind of saved one of the most interesting applications for last. With all of the tools that we've learned throughout these 2 weeks, throughout these 12 prior lectures, we are now able to solve for things like the inverse Laplace transform, which involves a pretty gnarly integral in the complex plane. Okay, so I'm not going to sugarcoat it. This is not going to be the easiest lecture you've ever seen in complex analysis, but it's very, very useful, very, very important, and it's going to show you how to solve for these super important inverse Laplace transforms. And I'm going to try to guide you through the high-level steps that matter, why we are making the choices we're making, how these things work together, but I'm also going to show you the nitty-gritty details. Okay, so this is going to be a little bit like going to the gym or eating your broccoli. It's going to make you stronger. Good thing we love our broccoli and our kale. So I like to ask my students, why do we care about the Laplace transform in the first place? Maybe I'll just write down the inverse Laplace transform, and then we will talk about it a little bit. So the Laplace transform takes a time domain function and maps it into a kind of generalized frequency domain function. So it's kind of a generalization of the Fourier transform for a certain class of problems. And to get back from that frequency domain back to the time domain, I need to take the inverse Laplace transform, which we call L inverse of some function f hat, which is a function of that complex variable or frequency domain variable s, my Laplace variable. And this is usually defined as 1 over 2 pi I. It's a super hairy integral. I'm going to write it out. 1 over 2 pi I integral of gamma minus I infinity to gamma plus I infinity. I'll tell you what this means in a minute. Of my frequency domain function f hat times e to the st ds. And this is the definition. When I put that triangle up there, you know that I've kind of just pulled this out of my hat. This is the definition of the inverse Laplace transform. So again, if I have a time domain function, I Laplace transform it to get a frequency domain function. And to get back to the time domain, maybe I take my ordinary differential equation and I Laplace transform it to make it easier to solve, and I get my transfer function and my solution. Then I inverse Laplace transform to get my solution as a function of time. This is the inverse Laplace transform function. And specifically, there are some conditions on this. So this gamma here, this is an integral in the complex plane. You see this goes from minus I infinity to I infinity plus a gamma. Gamma is chosen to be greater than the real part of all the poles of f hat. So poles are just things like 1 over s minus 5. There would be a pole at s equals 5 where it's not analytic. That function's not analytic. And I need gamma to be bigger than the real part of every pole of this function. And I'll draw you a picture in a minute, but this is a condition. We also assume that t is strictly non-negative. T is greater than or equal to 0. So this works for positive time into the future. So I'm going to show you how to compute this integral using things like Cauchy integral formula and the ML bound and things like that. But just kind of philosophically, I'll give you a little bit of a recap of why we care about the Laplace transform. We use the Laplace transform all the time when we're solving ordinary and partial differential equations. Specifically, partial differential equations that are parabolic, like the heat equation, where you can solve for them forward in time but not backward in time. Those are going to be very amenable to using the Laplace transform for solution. We also use this all the time in differential equations to transform differential equations into algebraic equations that are easier to solve, kind of with high school math. And then you inverse Laplace transform those to get the solutions back in time. Also very useful in control theory. If you have input-output systems, you Laplace transform both sides, the outputs of the system and the inputs of the system. And if you take that ratio, that's the transfer function. That tells you if I give a sinusoidal input, what happens to the output of the system. Very useful for control systems. And probably one of the most interesting and useful functions that we might want to inverse Laplace transform. So usually if you open up an engineering math book, almost all of them have a big table in either the front or the back cover of all of the forward and inverse Laplace transform pairs. And oftentimes you just are told to memorize these and expected to memorize them. And I mean, that's okay, you can remember what these things are, but I want to show you how to actually derive from scratch what the inverse Laplace transform is. So one of the most important inverse Laplace transforms we care about, so a specific example is the function f hat of s equals 1 over s minus a, where a is often a real number, a equals 2 or 4 or -1, okay? This is a Laplace transform function, a frequency domain function, a transfer function that comes up all the time in differential equations. This is in fact the transfer function for the simplest differential equation, x dot equals ax. Okay, and so for example, if I Laplace transform this differential equation, I get, the Laplace transform of x dot equals sx. Technically it's this is x hat. It's sx, minus my initial condition x at time 0, but I'm going to neglect that. And so if I say the Laplace transform of the left-hand side is sx, the Laplace transform of the right-hand side is a x hat. And if I collect all of my x hats on one side, then I get x hat equals, so this would be s minus a times x hat equals, I need that initial condition. Let me do this, sorry, minus x naught. And that whole thing equals a times x hat. This is actually the Laplace transform of x dot. You should be catching me on this. You should be yelling into your monitors. So the Laplace transform of the left-hand side is s, the Laplace variable times x hat, the Laplace transform of x minus my initial condition. And that equals the Laplace transform of the right-hand side, which is a x hat. And now if I collect all of my x hats, I get s minus a x hat equals x naught. And so I can rewrite that as x naught over s minus a. So this transfer function 1 over s minus a comes up all the time. It's the transfer function for the simplest differential equation with initial condition x naught equals 1. Okay, that's what this transfer function is. And I want to, now that I've transformed my solution to find this transfer function, now what I want to do is I want to inverse Laplace transform to get x as a function of t, the solution of my differential equation. So I would inverse Laplace transform, kind of L-1, to get x of t. This was in the Laplace variable. This is x hat as a function of s. Here, I inverse Laplace transform this now to get x as a function of t, which again, from differential equations, we know that the solution is just x naught e to the a t. So we know that this is the answer. And in principle, that means that we know that the inverse Laplace transform of 1 over s minus a is equal to e to the at. But I want to show you how to actually solve this inverse Laplace transform using this integral formula in the complex plane. Because not all differential equations that we come up against are going to be as easy to solve. Like, I just wrote down the solution of this differential equation off the top of my head. We know the solution of linear differential equations, x dot equals ax, are e to the at times the initial condition. So I didn't technically need to Laplace transform and inverse Laplace transform, but lots of times there will be differential equations that are hairy enough and gnarly enough that I really will want to use the Laplace transform and inverse Laplace transform to find the solution. So that's what I'm going to do. I'm going to derive today for you using everything you learned from complex function theory. I'm going to derive that the inverse Laplace transform of this transfer function, this very important transfer function, is e to the at. And we're going to do that using integrals in the complex plane. That's what we're doing today. Good. And I'm going to start by cooking up a really big, gnarly contour integral for us to do this inverse Laplace transform. Okay? So I'm trying to think of where I'm going to write this down. I'm just going to erase this, and then I'll probably fast forward. Okay, good. So I'm going to write down this specific inverse Laplace transform integral for this specific transfer function that we're going to walk through today. And then we're going to make an attack plan for how to actually solve this in the complex plane. So the specific integral we're going to solve is the inverse Laplace transform of 1 over s minus a. And so I'm going to plug in 1 over s minus a for my function f hat. That's my function f hat. So this is going to equal 1 over 2 pi I integral of gamma minus I infinity to gamma plus I infinity of my function 1 over s minus a times e to the st. E to the st over 1 over s minus a. And I integrate with respect to the Laplace variable ds. So this is the integral I'm going to be trying to solve, okay? And what's kind of cool about this is that this looks right out of the gate like exactly the kind of thing I would want to use the Cauchy integral formula for, okay? This is kind of the poster child for solving an integral with the Cauchy integral formula. Because I have so s is a complex variable here. S is kind of my z variable. And so this is an analytic function in the numerator. This is an analytic function divided by s minus a, kind of a transfer function with a simple pole at s equals a. So this is exactly what we want to solve using the Cauchy integral formula. And so I'm going to write down a couple of, I'm basically going to draw the contour integral that I want to solve, and then we're going to make an attack plan for how to do this using everything I've told you about the complex plane. So what I'm going to do is I'm going to draw in the complex plane here. Okay, so this is the complex plane. We have this pole at s equals a. And so I'm just going to choose arbitrarily a place to drop down my pole. We're going to say that this is where my pole a is. I'm going to just for now say it's real valued. It doesn't have to be real valued. I'm just going to say it's real valued and positive. So it's an unstable pole, and I'm going to inverse Laplace transform that system. So one of the kind of technical details of the Laplace transform, and you can go back to my video on the Laplace transform to see, is that when you do this integral, you need this gamma to be to the right. It has to have a real part that's bigger than the real part of this pole A in this transfer function. So that line gamma, so essentially this integral is along this big vertical contour integral that is offset from the imaginary axis by gamma. So this is kind of, gamma plus I omega or something like that. And this is the integral that I want. I want this big integral here. That's what I've written down here. And so the strategy that we're going to take is that we are going to essentially create a closed contour around this pole, because we know how to solve integrals of closed contours of an analytic function divided by a simple pole. So what I'm going to do is I'm going to connect like this. I'm going to have a kind of contour. I'm going to call this C+, and I'm going to have this contour I'm going to call C-. and then I'm going to draw a big circle. So this is the classic integral that people use to solve this problem. There's other ways of doing it, but this is kind of the classic one because it's the easiest approach, where now I would draw a big radius circle here, CR. Okay, and if I take the integral I want, let's call this just CI, the integral I want, C1. If I take C1 plus C plus CR plus C minus, this closed contour, we know that we can compute that closed contour by the Cauchy integral formula. It's going to be a simple expression. And if I took the limit as the radius goes to infinity, if I blew this up so that the radius goes to infinity, then this portion of that contour is the thing I want. It goes from gamma minus I infinity to gamma plus I infinity. And so that's how we're going to approach this problem. Let me annotate this a little bit. This is literally, this here has a radius r. Okay, this point here is gamma plus IR. This point here is gamma minus IR. And what we're going to do, I'll just write out the integral we're going to solve. We're going to say, this is called a Bromwich integral, by the way, a Bromwich integral, not to be confused with the Bromwich integral. The Bromwich, I don't know if any of you remember this, the Bromwich is one of the tastiest but most evil sandwiches known to humankind, made with wheat harvested from hell's half acre, mayonnaise made from the eggs of a deranged chicken. This is why I actually wanted this to be the 13th lecture. This is not the Bromwich integral, this is the Bromwich integral. In Texas, there is a dairy chain called Brahms that does make sandwiches, and those Bromwiches are delicious. This Bromwich integral is this full, large, closed contour that I'm drawing, this kind of backwards D. We're going to call that C, we're just going to call that C. That's our contour C, which is our Bromwich integral. And what we know, because of Cauchy integral formula, is that we can solve the integral over this closed contour, this big closed contour, for any radius that encapsulates this, for any radius at all, actually, for any radius. This closed contour is going to include that simple pole at s equals a, and I can use the Cauchy integral formula to say that the integral of e to the st over s minus a ds around that closed contour is equal to e to the a t. Now I'll just refresh what this is by, let's write this down, by the Cauchy integral formula, which I believe was just a couple of lectures ago I showed you this Cauchy integral formula, which says if you're integrating an analytic function in the complex plane divided by a simple pole, s minus a or z minus a, and I'm integrating it in a closed contour surrounding that pole, I take the analytic function and I evaluate it at the pole, and that's my answer. And this is times 2 pi I. I'm sorry, I should have absolutely, this is times 2 pi I. That's what this contour integral equals. And since I have divided by 2 pi I here, those are going to cancel, and this integral is going to equal e to the at. So let me just show you, I've kind of held back the last piece of the logic of the puzzle here, and I'm going to show you that right now, which is the following. This contour integral, maybe I'm just going to do 1 over 2 pi I out here, because this is 1 over 2 pi I, and I'm just going to get rid of this here. This contour integral, which is easy to solve, so this is easy to solve using Cauchy integral formula. We can just write down the solution of this contour integral around the whole Bromwich contour is e to the at. And we know that this is equal to the integral of the thing I want, contour 1, plus the integral of c plus the integral of c minus, plus the integral of cr. Okay, so this big Bromwich integral is the thing I want, this integral from gamma minus I infinity to gamma plus I infinity, plus this little positive segment, plus the big radius segment, plus my little negative segment. So it's 4 integrals that I've stitched into one mega Bromwich integral. And what I'm going to show you is that this equals, so let's say in the limit as r goes to infinity, C1 equals what we want. And I'm going to prove that all 3 of these integrals add up to 0. That in the limit as the radius goes to infinity, as I scale this thing infinitely large so that this C1 becomes the integral I want, this C plus and the C minus are going to be 0, and the CR is also going to be 0. So plus 0 plus 0 plus 0. And what that shows, kind of the logic here, is that I can compute this big Bromwich integral easily, and it equals e to the at. And that, in the limit as r goes to infinity, is equal to my integral that I want, which shows, it proves that this integral that I have here is going to equal e to the at. Okay, so that's the punchline. That is by far, that's the headline here of this story, is that if I can show that these 3 integrals equal 0 in the limit as r goes to infinity, we have then proven that this is the inverse Laplace transform of 1 over s minus a, which I kind of showed you from differential equations. This is in fact the inverse Laplace transform, but we are going to use complex integrals to show that. Okay, so all that we've used right now is we've cooked up a complex, big, gnarly contour, the Bromwich contour, that I can break into 4 pieces. And solving for each of these 4 pieces is going to be the hard part. But once I've made this big contour integral for any radius r, I can use Cauchy's integral formula very, very easily to show that the full Bromwich integral equals e to the at. So if I can show that this segment, and this segment are 0, then this full contour integral that was easy is just equal to my Laplace transform, my inverse Laplace transform integral. Good. That's the high-level logic. And now for the next, 10, 20 minutes, I'm going to show you piece by piece that these 3 integrals are equal to 0, which then will prove that this inverse Laplace transform equals e to the at. And then I'll do a quick recap. OK, so that's what we're going to do now. And I'm going to jump right in. It turns out that these ones are kind of easy, so I'm going to show those first. We're going to use the ML bound to show that C plus and C minus go to 0 in the limit as r goes to infinity. OK, so integral of C plus and integral of C minus, we're going to use the ML bound, which is kind of one of the easiest integral theorems in complex analysis. It's very trivial. So the length of this integral path is always gamma. Length is always gamma, regardless of the radius. The radius could be 2, it could be 10, it could be 1,000,000. All that's going to do is change the size of C1 and the size of this radius, kind of scale it up and down. But the length of C plus is always gamma, and the length of C minus is always gamma. So L is the L in the ML bound is always going to be gamma. And so now what I have to do is I have to bound this portion of my integral. And I have to show that this kind of gets smaller and smaller as my radius increases on this segment. So I'm just going to do this for C plus. So for C plus of e to the st over s minus a ds, what we have, this is equal to the integral. I'm actually going to write out what this integral equals. It's the integral from gamma plus IR to just IR, right? We're just moving kind of in this real direction from gamma plus IR to IR. Again, of e to the st over s minus a dt, nope, ds, sorry, ds. And so essentially, again, I'm going to use some shorthand notation here to say that this is an integral from gamma to 0 of e to the x plus IR. I'm just saying that my variable s equals x plus IR on this little segment where x varies from gamma to 0. That's pretty straightforward. On this little segment, my complex variable is x plus IR. The imaginary part's always held constant at IR. And x varies from gamma to 0. So I'm integrating from gamma to 0 of e to the x plus IR t divided by x plus IR minus a. Dx now, not ds, dx. And I'm going to check my notes because this could be something I would make a mistake on, but this is correct. And what we're going to show is that this is less than or equal to some m L bound. So the length of this is gamma. We're going to show that this quantity is equal to is no greater than m on that whole path. And we're going to show that that m gets smaller and smaller as r goes to infinity. That's how ML bounds work. And it's really kind of elegant and simple. And so m is the max of x between 0 and gamma of e to the x plus IR t divided by x plus IR minus a, kind of the magnitude of this. This is, again, what we're doing for ML bounds. And I'm going to claim that this quantity is always less than or equal to e to the gamma t over r. Now, how do I want to do it? Remember, we're going to use this a bunch in this lecture, so I'm just going to write it down. This is e to the real part plus imaginary part, e to the xt plus IRT. So if I have e to the xt plus IRT, this is going to equal e to the xt times, this is from Euler's formula, cos RT plus I sine RT. And very important property, this has norm equal to 1. For any RT, cosine something plus I sine something, the magnitude, the length of this vector is always equal to 1. So the length of e to the xt plus IRT is always equal to the magnitude of the real part, e to the xt. Okay, this is the magnitude. So the magnitude of this quantity here, the biggest it can be, is when x equals gamma. So the maximum magnitude of this numerator is e to the gamma t. Pretty straightforward. If that was a little fast, just rewind and go through it again. This is a cornerstone property of complex numbers that, e to the u plus iv equals e to the u times cos v plus I sine v. And this iv, no matter what v is, it can't contribute to the length of this vector. It doesn't contribute at all to the length of this vector. V is essentially the angle, and the length of the vector, or the radius, is just e to the u, the e to the real part. Okay, and so the max value that this can, that the length of this vector can take is e to the x when x is gamma. Okay, so that's what we have here. And similarly, down here, the largest length that this can have is, let me see, x plus IR minus a. Okay, so if I have, the biggest this can be is if x equals a. If x equals a, then this is 0, and that minus kind of gets canceled out. And this thing is going to be, something which is on the order of length of r. Let me, is that 100% correct? If x is between 0 and gamma, and this is a fixed number, then if I make r really big, then this quantity is going to dominate over those two. And so this numerator is essentially going to be an r. So what am I trying to say? Yeah, the length of this thing, sorry, I'm mixing myself up. This is important though for you to see me get confused, because this is confusing. this numerator is always less than or equal to e to the gamma t. Good. And in fact, its maximum value is exactly when x equals gamma and is exactly e to the gamma t. So this should be, for the numerator, that's an equality. That's the maximum value. And it's divided by something. And the max of this thing is attained when the denominator is the smallest length it can possibly be. And this thing has its smallest norm or length. Normally, it would be r squared plus x minus a squared square root. And so if x minus a is non-zero, this thing is actually a really, really big radius. You know, it's a bigger number, it's a bigger length. And so I'm saying that the maximum value is when this has its smallest norm. This has its smallest value when x equals a. And when x equals a, which is in this interval, then the norm of this is exactly equal to r. Okay, so that's, again, that was a little bit confusing, a little bit fast. You might want to rewind that last 2 minutes if you think so. So to find the max of this whole length, I'm trying to find the value x where the numerator is as big as possible and where the denominator is as small as possible. The biggest the numerator can get is e to the gamma t when x equals gamma. The smallest the length of the denominator can get is r when x equals a. So this is the ML bound. M, everywhere on this curve, my function has length no larger than e to the gamma t over r. And the nice thing about that is that now m and l, so m is e to the gamma t over r, l is a constant gamma. So if I take the limit as r goes to infinity, this thing goes to 0 because I'm dividing by infinity. I'm dividing a constant number times a constant number divided by infinity goes to 0. That proves that c plus, the plus part of my contour, this integral equals 0. And the c minus is exactly the same. I'm not going to like do a whole nother thing just for c minus. It's exactly the same. So both of these plus and minus portions of the integral equals 0 in the limit as my radius goes to infinity, as this thing gets bigger and bigger. Okay, so those two are done. And now I have to show that this big CR contour also goes to 0. I'm going to erase my board, and that's what we're going to do next. Okay, so now I'm going to solve the hardest part of this. Okay, so bear with me. This was never going to be easy, but this is important, okay? Like we just spent 2 weeks learning all this interesting complex function theory and how to integrate in the complex plane. And this is an actual legitimately useful and important application here is to solve the inverse Laplace transform. And so I really want to get to show you. So now I'm going to show that this big radius portion of the curve goes to 0 as my radius goes to 0. So I'm going to show that this equals 0. This one's going to be a little bit trickier. So ML bounds for integral of CR, ML bounds don't work. At least I've never been able to get it to work, don't work. And so we're going to use some tricks. These are tricks that I must have picked up somewhere in my education. I don't remember where I got these. You will someday forget where you learned them. But the basic tricks is we're going to try polar coordinates. And that's why we extended this. Instead of just having a big radius coming directly from C1, that's why we had C plus and C minus to move these over to a place where we could actually use polar coordinates. So this point is going to be r, e to the I theta. So there's going to be an r cosine theta and an r sine theta. So we're going to say x equals minus r cosine theta, and we're going to say y equals r sine theta, and we're going to do an integral basically from theta equals minus pi halves to pi halves, something like that. Okay, we'll see, and you'll have to check that I'm doing the right bounds of integration. And so essentially what we're doing is, we're solving for this portion of the Bromwich integral here, where theta is going to start at and I'm really abusing polar notation here. I'm calling this minus pi halves because I have a minus r cosine theta, and I have, this goes to theta equals plus pi halves, and it's going counterclockwise. I am pretty sure there's a better way of integrating from plus pi halves to minus pi halves with a plus r cosine theta. And maybe I should do that, but I'm just going to stick with my notes. And maybe as an exercise, you can try to, use the normal polar convention of x equals plus r cosine theta and change this to theta equals plus pi halves to minus pi halves. I think, we're pretty good at changing the definition of where things start and what's positive and negative. So I think this will be OK. And so we're, again, trying to kind of show what the properties of these two terms in this integral are across this contour from theta equals minus pi halves to pi halves. So I'm going to isolate this and break this up. I have the, maybe I'll switch colors to make it a little more interesting. So I have my e to the st portion. I'm going to look at the norm of that. Again, the length, the norm, if I have my st has a real part, let's call that, x plus I, y, the norm of, e to the st, the norm of that is going to equal e to the x. It's going to be the length of e to the real part. So the norm of this is going to be minus r, e to the minus r cosine theta. That's going to be the norm of this thing. So that's e to the minus r cos theta t. That's the norm of the numerator, is this thing here. And the norm of s minus a, the denominator here, is similarly going to equal the norm of, and I'm just going to plug everything in here. I think it's minus r cos theta plus I r sine theta minus a. And I put the minus a here because I'm going to group these real valued parts and this complex valued part separately. But the s is the r cosine and r sine, and the a is right here. Okay, so that's the norm. And that norm is equal to, this is kind of a mess, but it's the square root of r cos theta plus a, quantity squared, plus r sine theta, quantity squared, the square root of that. It's literally the norm of this is the real part squared plus the imaginary part squared square root. That's this. And if I do a little fancy arithmetic here and I cancel out some stuff, I'm going to get an r cos squared and an r sine squared. Those are going to add up to an r squared. So I'm going to get an r squared. I'm going to get a plus 2r cos theta plus a squared. Okay, that's what all of this simplifies to. You can verify that. And I'm going to claim that this is always greater than or equal to r minus a, to the norm of r minus a. Okay? Why is that true? So this is kind of well, the norm of r minus a is r squared plus a squared minus 2ar. And this is, I'm sorry, I missed an a when I expanded this out. This should be 2r times a times cosine theta. And yeah, so the norm of r minus a is just r squared plus a squared minus 2ar. So it looks almost identical to this, except that up here, this 2ar is multiplied by cos theta. And cos theta can never be bigger than 1. So this expression is always strictly less than or equal? Yeah, this expression here is always, this should be a greater than or equal, I'm sorry. This should be less than or equal. This expression here, the length of this, r squared plus a squared. I'm sorry, I'm like, it's been a real wilderness of complex variables. This was correct. I want you to really see why this is true. So I'm going to derive this. I'm going to show this again. This is the hardest integral, so it makes sense that we're getting a little confused here. We're going to do something kind of like the ML bound. We're finding the norm of this and the norm of this, and I'm going to use some argument to show that as r goes to a large number, the ratio goes to 0, something like that. And so I need an expression for the norm of s minus a, and I've done some math, and I've done a trick, and I've done another trick. And now I am showing that this expression here is always bigger than the norm of r minus a. The norm of r minus a is this quantity here. And this is minus 2ar. So this thing is always, detracting from the norm. It's making it smaller. And unless cosine of theta is exactly equal to -1, this term is detracting less, or maybe even adding to the norm of r minus a. So I want you to just think about why this is always bigger than or equal to this, because of the properties of cosine. So if cosine is -1, then this equals this. But if cosine is anything bigger than -1, it goes between -1 and +1, this expression is greater than this norm here. And we're going to use this property kind of like we use the ML bound. Good. Okay, so that is very useful. And so what this means is, I'm going to say the integral over CR of e to the st over s minus a ds is, let's say that the norm of this whole thing is strictly less than this integral. We're going to now integrate over thetas because we've gone to polar coordinates. The integral with respect to theta of this thing, e to the minus r cos theta t divided by norm of r minus a times, and we're integrating from minus pi over 2 to pi over 2 d theta. And last important thing, when we're integrating in polar coordinates, this is r d theta, because we are at a radius r, and so we're going r times d theta is, every little segment here, ds, is r d theta, because we're at a big radius r. Okay, this is radius r. And so now what we're going to try to do is we're going to try to show that this thing goes to 0 as r goes to infinity. Okay, and we can also even simplify this more. We can, this is an even function. This is an even function. And so we can say that this equals 2r over r minus a norm integral from 0 to 2 pi, pi, pardon my French. Pi over 2, Laplace was French, of e to the minus rt cos theta d theta. We're integrating with respect to theta. We pulled out the r's. This is a really ugly pi over 2. And I was able to do this. I was able to do this integral to say that this integral from minus pi over 2 to pi over 2 equals this, because it's an even function. So I picked up this value of 2. It's twice this half of that even function. Okay, we're getting really close. Thank you for bearing with me just a little bit farther. If this is just boring you to tears, you can skip to the next chapter mark, but I would stay with me because we're almost there. And so there are a couple of other tricks we're going to do here. Basically, we're just going to keep doing tricks until we can force this thing into a reasonable solution. So the last trick is that cos theta is always greater than or equal to 1 minus 2 theta over pi on the interval theta between 0 and pi halves. Okay, on that interval. And so e to the minus r cos theta t is always less than or equal to e to the minus r t times this value here, this 1 minus 2 theta over pi. Good. And I could make my minus go in here and say that that's, of course, equal to e to the r t times 2 pi over theta, 2 theta over pi minus 1. Okay, so I've just used kind of every trick at my disposal, every trigonometric trick I have. You can, again, verify that this is true. This is just like kind of a basic trigonometric fact that you should verify if you don't believe me. And so finally, this integral here, we're going to say is this thing here is less than or equal to 2r over norm of r minus a of this integral, which is 2r over norm of r minus a of this integral from 0 to pi halves of now this expression here, e to the rt theta 2 theta over pi minus 1 d theta. It's actually strictly less than or equal to this. And this is something we can actually solve. This is now an integral e to the theta constant plus a constant d theta. We can actually solve this closed form, so we're basically there. And that equals 2r over norm of r minus a, pi over 2rt e to the rt 2 theta over pi minus 1. This whole thing evaluated at the bounds of integration pi over 2 and 0. And if you plug all of this stuff in here, so at this point this just became a standard integral you do know how to solve. This is the answer. We're going to evaluate it. And that just equals pi over norm of r minus a t 1 minus e to the minus r t. And e to the rt, e to the minus rt as r goes to infinity, this goes to 0. So this whole expression goes to 1 as r goes to infinity. And pi over norm of r minus a, the norm of r goes to infinity as r goes to infinity. So this whole thing goes to 0 as r goes to infinity. Whoa, that was a mess, okay? This is a nightmare. That's why I think of this as the Bromwich integral, because this is the most evil integral. You had to use so many tricks to get this this big radius CR to go to 0 as r goes to infinity, but it is technically possible, right? So we used we switched to polar coordinates, we derived these expressions for what these numerator and denominator are bigger than or smaller than, and then we did more trig substitutions, but eventually we showed, and you'll have to check my steps, like I expect my students to actually check these steps that I did in the middle just to really convince yourself and kind of go back and see why I was doing it in the first place. Okay, good. So that was the tough part. Now I am going to summarize everything. So the big summary here is that I'm trying to solve this inverse Laplace transform integral because that's super duper useful in differential equations, both ordinary and partial, in control theory, and in tons of other fields of engineering, is to be able to Laplace transform and inverse Laplace transform. And specifically, if I want to inverse Laplace transform something like this function 1 over s minus a, which comes up all the time in linear differential equations, I essentially need to solve for this very, very large vertical integral in the complex plane, the integral from gamma minus I infinity to gamma plus I infinity. And so what I do instead is I create a large closed contour called the Bromwich integral that has the integral I want, C1, plus 3 other segments that I don't want. But I close this loop around that pole so that I can use Cauchy's integral formula. Because I can integrate this closed contour integral around C of my function I'm trying to inverse Laplace transform easily using Cauchy integral formula. It's essentially trivial because this is an analytic function and it's divided by a simple pole at s equals a. Then the closed contour integral of everything equals e to the at. And that's the sum of the integral I want plus this little segment plus this little minus segment plus this big radius contour here. And so if I can show that in the limit as r goes to infinity that these 3 terms go to 0, And in the limit as r goes to infinity, this segment becomes the integral I want. So if I can show that these three go to 0, then the integral I want equals e to the at. And we showed, it took, I guess, 25, 30 minutes, that these three integrals equal 0 in the limit as r goes to infinity. So therefore, we have shown that the integral we want, the inverse Laplace transform by Cauchy integral formula and some heinous math, is equal to this e to the at. So that's super duper cool. And I think now you are armed with some of the most powerful tools in mathematics. You know how to integrate in the complex plane, you know how to differentiate in the complex plane, and now you can solve, these are some of the nastiest integrals out there. If you can solve these, you can solve anything. All right, I'm really proud of you all for sticking with me through 50 minutes of complex integrals, Bromwich integrals. This is the real deal. I'll see you next time. Thank you.